Good evening, everyone. Thanks for joining in today's webinar. Am I audible? Whether my voice is clear?
Yes, you are audible.
Yes, sir. Thank you, sir. In today's webinar, we will be concentrating mainly on earthing for substations. We have already conducted separate webinars for lightning protection system, risk assessment calculation, designing of lightning protection system specific for high-rise buildings and solar industries, and overview of earthing, and myths and misconceptions related to earthing, a separate webinar. And we have uploaded those videos in our YouTube channel. So if you want more clarification about those topics, you can refer to our YouTube channel. And if you have any queries, you can contact us at any time. In today's webinar, we will be concentrating mainly on earthing for substations, how we are designing earthing for substation, how the earthing for substation is different from the other earthing for the equipments and other for factories. So before entering into topic, let us provide a small introduction about CIKIT. CIKIT was incorporated in 2018. Even though it is a 6 years old company, we are having an experience of more than 17 years in this field of lightning protection and earthing. Our specialization is we are providing end-to-end solution for both lightning protection system as well as this earthing. So end-to-end solution, which includes performing site analysis, performing risk assessment calculation for lightning protection system, designing of lightning protection system, material supply, installation, maintenance, and auditing of the existing systems as well. So in case of lightning earthing, we are providing the service related to maintenance of earthing system, performing the soil resistivity calculations also, apart from the other activities. And our one more specialty is we are providing customized solution rather than going for a generalized solution, which includes when we are working for some specific industry, then we will be referring to the standard that is very specific to that particular industry rather than going for a generalized standard. So if you take lightning protection system, 62305 is a standard which we are generally using for the designing. But when we are working with oil industry, we will be referring to the standard that is very specific to the oil industry. So Oil Industry Safety Directorate has published a set of rules. So when we are working with oil industry, we will follow that particular regulations that are specific to oil industry rather than following the 62305. So this is one of our specialty. As I mentioned, these are some of the standards which we refer related to earthing. So the IS 3343 is the code of practice of earthing which we follow for designing the earth pits for all the kind of applications. BS 7430 is the British standard. IEEE 80 is the standard which we use for designing this earthing for substations. And UL 467 explains about this requirements of earth electrodes, and if you take this copper bonded rods and STGA rods, they have clearly explained about what are all the different tests that has to be done and what are the requirements of that copper bonded rods and STGA rods. And the second one is the last one is 62305, which explains about this earthing requirements for lightning protection system. 62561 part 7 has explained about requirements of earth enhancing compounds. So these are the different standards which we will follow for designing this earthing. So in today's webinar, we will be concentrating on IEEE 80. So IEEE 80 is the standard which explains about this designing of earthing for substations in detail. So before going into the detail, first we need to understand our different stages in the power system. So the power system is one of the most complicated topic in, and if you take India, the transmission lines are running across the country from each and every part. So if you take these different stages, the first stage is power generation. So the power generation stations will be located at a remote areas. Nowadays we are having the solar power and we are generating this power locally. But in earlier days we won't have the solar power and all. We will have only the thermal power stations, hydro power stations, and nuclear power stations. And all these power stations will be located in a remote area, and we will be generating the power at the remote stations. And we cannot transfer this power at the voltage that is generated. So we will step up this voltage to higher levels, and we will transfer this energy from one part to another part. So there are so many reasons for stepping up to higher voltages, and one such reason is to reduce the losses and all. So the power generated won't be transferred at the same voltage which we are generating. So we will step up that voltage to higher level, and at the using end we are using single phase 240 volt, and if you take this 4 volt means it will be coming as 440 volt and all. So if we are stepping up to that higher level, then in between stages we have to step down. So the substations or the locations where we will be stepping up and stepping down this voltage levels. So based upon the requirements, we will be having multiple substations. So the first stage of power system is the generating station, and the second stage is nothing but the transmission, where we are transmitting this energy from one area to another area, and the final stage is nothing but the distribution, where the energy is distributed to all the consumers. So in this entire process, we are stepping up and stepping down this voltage levels at multiple places, and the location where the stepping up and stepping down is taking place are called as substations. So substation is the actual place where we are taking transforming this voltage from one level to another level. So if you take one particular system, there will be lot of substations involved. And why we are giving more importance to substation is the power related to this particular substation is very much higher, and it will be very difficult to handle those huge amount of power. If I take one particular industry, the power operating capacity will be much lower, but for that particular industry, we will be taking power supply from a substation, and in that particular substation, there will be hundreds of industries will be connected. So the substation, which is feeding these hundreds of industries, will be handling the entire amount of energy required for this 100 industries. So the power rating of those substation will be very much higher, and the fault current rating of the equipment in the substation also will be very much higher. In our industry, if any equipment fails, it will result in the loss of production for this particular wing alone. But if any equipment in the substation fails, then if 100 industries are fed, means all the industries, 100 industries won't receive the power supply. So any failure in the substation will result in loss of service to all the industries which are receiving power from the particular substation. So substations are very much essential, and a failure in substation will result in loss of service to the entire area also. So this is the transmission line network of India, and here also we have taken images with lines operating 400 kV and above. With 400 kV and above itself, it looks much complicated. But if I took all the transmission lines, we cannot see even the land also. That much complicated is our electrical network. And one more thing is here they have provided this blue dots. So these blue dots are the locations of substations. So from this image, you can observe that there are thousands of substations are present in India alone. So for all these substations and all, the earthing is very much essential for ensuring the proper operation of the substations. So this is a sample image of substation. So some of the commonly used equipment in a substation, or the first four component is the surge arresters or lightning arresters, which will be placed before this transformer for protecting this equipment from the surges. Second one, the commonly available equipment are the transformers. Then for measuring purpose, we will be using CT, PT. Apart from that, for isolation, we will be using this air brake switches, isolators. Then we will be having this circuit breakers. So apart from that, for operating the circuit breaker, we will be using lot of relays. So each and every substation will be having lot of components, and all these components will be designed for handling this much higher rating of power. And so why earthing is important, and how this earthing for substation is different from the earthing which we are providing for other applications. So if you take this earthing is nothing but we are providing a dedicated low resistance path for either the fault current or impulse current to discharge into the soil. So at normal operating conditions, there won't be any need for discharging this current. So the earthing is required comes into the picture when there is an abnormal conditions like fault condition or lightning impulse passage of conditions. So during this abnormal conditions, we need to discharge this energy into the ground for protecting this person as well as from the equipment. So the process of providing this dedicated low resistance path by connecting this particular equipment to the ground is called as grounding. So if you take this application, based on the application, we can divide this earthing into two types. One is system earthing, another one is equipment earthing. So everyone will be aware of the term equipment earthing. So if I'm having any machine, I will be connecting the body of the machine to the ground for the safety of the operator. So if I'm connecting this non-current carrying metallic part of a system to the ground, it is called as equipment earthing. So if you take the metallic enclosure, it is a conductor, but it is a non-current carrying conductor. So it won't be carrying current at all the time. So if we are having any plastic equipment, so for those plastic equipments as well, we won't be providing body earthing. We will be providing this earthing only if it is a metallic enclosure. So connecting the body of the equipment to the ground is called as either equipment earthing or body earthing. And the second type is connecting the current carrying conductor of a system. So if we take this system, the neutral will be considered as current carrying conductor. So the current will be always flowing through this neutral. It might be either this unbalanced current or some other current. It will be always some amount of current will be flowing through this neutral. So neutral is considered as the current carrying part of a system. So if I'm connecting the neutral of the system to the ground, it will be considered as system earthing. So if I'm going for this substation, it contains both system earthing as well as this equipment earthing. So usually the transformers will be connected to the yet only at the substation area. So the system earthing comes into picture when we are going for this substation. And similar to equipment earthing, we cannot use the sizing randomly for the system earthing. So the sizing has to be done properly and based upon proper calculations, we have to select a suitable size for this earthing of transformer neutrals. So if we are going for this earthing, the ultimate aim for providing earthing is the safety of operator. Because if you take any equipment in industries, if any person makes contact with the equipment which becomes live, he will get electrocuted. But the problem with this substation is, even if you are not having any direct contact, the person who is working inside the substation may get electrocuted. So in this substations, the ultimate aim of providing this earthing is to maintain the step and touch voltages within the limit. So if you take this touch voltage, for this touch voltage you have to make contact, but for the step voltage there is no direct contact itself is required. Even if some person is walking in the substation area, if the ground potential is higher and if there is a sufficient potential difference between the 2 foot of this particular person, he may get electrocuted. So if I'm working with substation, the most important parameter is the step and touch voltages. We need to ensure that the step and touch voltages are within from the electrical hazards. So if we take this earthing, the most important component is the earth electrode. So the purpose of this earth electrode is to dissipate the fault current into the soil. So if we want to dissipate it, it should be able to withstand the fault current. So the primary purpose of earth electrode is to dissipate it, and hence it should be able to withstand the fault current without any damage. So proper sizing calculation should be done for selecting the size of this earth electrodes. So it should be able to withstand the fault current, and most importantly, it should have good corrosion resistance property. So everyone knows that aluminum is a very good conductor, and for all the transmission networks, we are using aluminum. But for earthing, we won't use aluminum. So even though aluminum is a very good conductor, because of its corrosion resistance property, we are not using aluminum for this earthing applications. So one of the important parameters or properties of the earthing conductor should be, it should have good corrosion resistance property. So when we are explaining about this earthing, the first question that will be coming to the mind of everyone is the earth electrode resistance. What should be the earth electrode resistance? So many people will be having an idea that for if a system is working good means then the earthing resistance value should be less than 5 ohms. Or in some cases they will tell if the resistance value is less than 1 ohm, then the system will be considered as good system. But that is not the case. So the resistance which we are explaining is generally the electrolytic resistance. So here we will be studying about the components, resistor, inductor, capacitor, and the networks and all. And if we are procuring any cables, for procuring the cables also we will be mentioning that resistance per unit length of the particular material. So here the resistance is nothing but the opposition provided by the material for the current to flow from one point to another point. Let us have one end as A and another point as B. So this component will provide opposition for the current to flow from one end to another end. Similarly, if I'm having a conductor of length L, so if a current is flowing means this material itself will be having some property to oppose the flow of current. So the current is flowing from one end to another end in the material. So here the conduction is taking place in the same material from one end to another end. So in this case, the material is providing some kind of opposition. So this will be considered as ohmic resistance. So the ohmic resistance is nothing but the opposition provided by the particular material for the flow of current from one end to another end. And here the adjacent materials or adjacent medium is not yet considered and it won't have any impact. But the second type of resistance is nothing but electrolytic resistance. In electrolytic resistance, for example, if I take earthing as an example, if fault current is flowing to this earth electrode, the dissipation will be taking place from this earth electrode to the surrounding soil. So here the dissipation takes place from one medium to another medium. So here the surrounding medium plays an important role. So in an electrolytic resistance, the conduction is taking place from one medium to another medium, and if the surrounding medium is having very high resistance, then the discharge won't be proper. So in electrolytic resistance, the surrounding medium plays an important role. So if you take this earthing, depending upon the soil resistivity, the value of earth resistance value will be different. So with one earth electrode of same dimension and same earthing compound, we cannot ensure that if you install this particular product on any kind of soil, you can achieve the same values. That is not at all possible, and we cannot do any magic for maintaining the same value. If you take one site conditions where the soil resistivity is 1000 ohm meter, and if we take another soil of 10 ohm meter, if I install the same earth electrode, for example, I am installing copper rod of 20 dia. So if I install this rod on these two conditions like 10 ohm meter and 1000 ohm meter, definitely the earth electrode resistance value will be different because the earth electrode resistance value mainly depends upon the soil and it does not depend upon the material which we are using. So definitely, since there is a huge difference in resistivity of soil, the earth electrode resistance value will be different. So standard has clearly mentioned that the resistance associated with earthing is electrolytic in nature, and in electrolytic resistance, the material resistance of the surrounding environment plays an important role. So here the surrounding medium is the soil, and hence the soil resistivity plays an important role in determining the resistance of earthing. So this is what happens during the discharge of fault current. So if any fault current is discharging from this earth electrode, the discharge is taking place from electrode to the surrounding medium. And if you observe closely, the potential which is very near this earth electrode will be very much high, and if you move away from the earth electrode, the potential reduces. So the points which are very close to this earth electrode will be of very high potential, and if you move away from this earth electrode, the potential reduces gradually. So this is how the potential will be. So here we are having this earth electrode and the current is flowing from this earth electrode. So the earth electrode will be at very high potential and the surrounding environment will also be a very high potential, and if you move away, the potential is reducing. So if you closely observe this, most of the potential is dropped in an area very near to this earth electrode. So that is the reason we are providing earth enhancing compounds surrounding the earth electrode, because most of the potential will be dropped in an area very near to this earth electrode. If I provide a highly conductive medium on that particular area, the performance of the earthing can be improved. So that is the reason we are providing earth enhancing compounds in the area surrounding this earth electrode. And if you closely observe this, the potential near the earth electrode will be very much higher, and if I move away from this earth electrode, the potential will be very much lower. So the sudden increase in potential during this discharge of fault current will be considered ground potential rise. So if we are mentioning a sudden increase in ground potential, means there has to be some comparison. So here the comparison will be between the potential of this particular earth electrode or with the potential of any remote earth electrode. In general case, we will be having this potential of earthing as 0 volt. So At the time of discharge, it won't be at 0 volt. There will be an increase in potential. So the level at which the potential is increasing will be considered as ground potential rise. So IEEE 80 has mentioned that the maximum electrical potential that a ground electrode may attain relative to a remote ground potential. So when I'm comparing the potential of this particular earth electrode with the remote earth electrode, there will be a huge difference in the potential. That huge difference in the potential will be considered as ground potential rise. So the potential is nothing but the voltage. So the voltage can be will be equal to grid current multiplied by the grid resistance. So I into R. P is equal to IR. The same is applicable here. Here the I is the grid current, whereas GR is the grid resistance. By using this formula, we can calculate the value of ground potential rise. So whenever we are discussing about the substations, along with the substation, four more important potentials will be coming into the picture. We will be concentrating mainly on two potentials, that is step and touch voltages. But apart from these two voltages, there are two more voltages also has to be considered. So if one person is standing inside this substation area and he is making a contact with this grounded object. So here you can see it. So here the person is standing here and he is making contact with the structure which is very high potential. So the person's foot is at low potential whereas the structure is at very high potential. So because of this difference in potential, the current may flow through the body and he may get electrocuted. So this is called as touch potential. So for this potential to cause damage, we have to make contact with the grounded object. So the second one is the step potential. So in this case, there is no direct contact between the person and the other structures also. So if you closely observe, this point is grounded and hence this point will be at higher potential and the potential is reducing. So the first foot will be at higher potential and the second foot will be at lower potential. So because of this difference in potential, the current will be flowing through the body and the person will get electrocuted. So for the step voltages, there is no need for direct contact also. Even without direct contact, he may get electrocuted if there is a sufficient potential between these two foot. So we have to clearly observe one thing, that the first criteria for the current to flow is the difference in potential. So if two objects are maintained at the same potential, then there won't be any current flow. So if whenever there is a difference in potential, then the current will be flowing from higher potential to lower potential. So the same thing is happening here. If the two foods are maintained at the same potential, then there won't be any current flow. So that is the reason if you are working in any substation, you could not run inside the substation. At the same time, you should ensure that there are very few distance between the two foods so that the step voltage will be much lower. So whenever there is a difference in potential, in that case only the current will be start flowing through that. So in the substation yet mat, what we are doing is we will be maintaining this voltage at the same level and we will ensure that there is no much difference in the voltage level. So if the potential is rising, then for the entire area the potential will rise and we will be maintaining this uniform potential throughout the entire area. So we have covered about two terms. One is step voltage and touch voltage. The another two parameters are metal to metal touch voltage. So in this case, the person is having contact with one structure which is at a higher potential and he is making contact with another structure which is having another potential. So because of this difference in potential, the current will be flowing from that high potential structure to the low potential structure through the body of the person. So here also the main damage is caused because of the difference in potentials. So if you closely observe this, in touch potential and metal to metal touch potential, the current is flowing through the body, through the hand, and the current will be flowing near to the heart area. But if you take the step voltages, the current won't be reaching to up to the heart. So the effect of step voltage will be very much higher than this. Sorry, the effect of touch voltage will be much higher than the effect of step voltage because the current will directly reach the heart area and it may result in unconsciousness or other death as well. So the fourth important type is the transferred voltage. So in this particular case, if you take one particular substation, there will be certain components which will be traveling from outside the substation to inside the substation. For example, there will be some pipelines which will be laid from outside the substation to inside the substation, and we will be grounding this substation at grounding this pipeline at different points. So the pipeline voltage will be different, and the potential at inside the substation will be different. So if some person is standing inside this substation and making a contact with this pipeline. Because of this difference in potential, he may get electrocuted. So this is considered as transferred voltage, and it will be coming into the picture when he is making contact with structures or any pipelines that is traveling from the substation to other objects and all. So when we are working with substation, we have to keep in mind about all these parameters to ensure that the safety of the person is maintained. So IEEE 80 has provided a detailed description about the designing procedure for this earth mapping. So the first step is field data collection. So we have to collect the details from the field. Second one is conductor sizing. Third one is step and touch voltage calculation. Fourth one is initial design of earth map. Fifth one grid resistance. Sixth step is grid current calculation. Seventh one GPR calculation. So here then we will calculate the actual step and touch voltages. Then we will be comparing this mesh voltage and tolerable touch voltage, and then step voltage and tolerable touch step voltage, and we will be making this modification if they are not within the limit. And if you closely observe this 12 steps, here we are not at all considering the earth electrode, that is the earthing resistance value or grid resistance value. So many people will consider that the grid resistance value should be less than 1 ohm, but that is not the case. Standard does not consider this resistance value for evaluating the design procedure. So they have considered two important parameters, that are step and touch voltage. So if the step and touch voltages are within the limit, then the design can be considered as safe, and it is not mandatory to ensure that the grid resistance value is less than 1 ohm. So why we are giving importance to grid resistance is only because of this GPR calculations. So when explaining about this GPR, I have mentioned that GPR is nothing but the product of Ig into Rg. So if the Rg value is maintained low, then because of lower Rg, the GPR also will be maintained low. If the GPR is low, then the step and touch voltages will be low. So that is the reason it is recommended to maintain lower grid resistance value, and they have not mentioned that the grid resistance value should be less than 1 ohm. It should be as low as possible, and for ensuring the design whether it is safe or not, they are considering only the step voltage and touch voltages, and they are not considering the grid resistance value as an evaluating parameter. So it is not mandatory to ensure that the value is less than 1 ohm. So the first step is field data collection. So the first thing is we need to visit the site and we have to check what is the available area for this earth map conditions. So if you take this substation, earlier days it was open space where there a lot of space will be available, but nowadays the space becomes there are so much constraints in the space availability. So first we have to go to the site and we have to check what is the space availability for installing this earth mat. And second important thing is the soil resistivity. So as I mentioned, if I am going for earthing, the earthing is mainly electrolytic in nature, where the performance mainly depends upon the soil resistivity. So the first thing that we have to consider is the what will be the soil resistivity on that particular site conditions. If the soil resistivity is good, very low means it will be much easier for our design. If the soil resistivity will be higher means we have to do higher calculations also. So if I am going for earthing, then the performance of earthing mainly depends upon the soil resistivity. So the second step is conductor sizing. So as I mentioned, the primary purpose of providing earthing is to dissipate this fault current. And if we are dissipating this fault current means the conductor should be able to withstand this fault current. If it is able to withstand, then only it can dissipate. So the standard has provided the formula for calculating the current carrying capacity of this particular conductors. So this is the formula provided by the standard. If you closely observe, the current carrying capacity mainly depends upon the cross-sectional area, then thermal capacity and different parameters. So one of the parameters is the resistivity, another one is the time. That is the clearing time. So the time is one of the important parameter when we are calculating this current carrying capacity. So if you take in general, the fault current rating of any substation will be mentioned as either 25 kA for 1 second or 20 kA for 3 seconds or 40 kA for 1 second. So whenever they are mentioning this fault current, they will always mention the duration along with this, because the current carrying capacity of the conductor mainly depends upon the duration. If the duration is higher, the current carrying capacity will be lower. For if I take one particular conductor as an example, the current carrying capacity of the conductor will be much higher for 1 second, but if I take 3 seconds, the current carrying capacity will be lower. So the duration of the fault current will be uh, one of the important parameters that has to be considered for calculating this current carrying capacity. So the standard has provided the different parameter values involved in this calculation, and they have provided the form parameters for different materials. So the different materials provided are copper, stainless steel, aluminum, copper coated steel, zinc coated steel, and all. So among these materials nowadays mainly we are going for this copper coated steels. We are mainly using copper coated steel nowadays for earthing applications, and because of this performance, at the same time, the cost is also cheaper than this copper. So nowadays, we are mainly going for copper casting. And another material which we are using for a longer period is the zinc coated steel rod. So in both this application, copper coated steel and zinc coated steel, the core material is the same. We are using steel as the core material, and both the cases generally we use MS material as the steel for the core. And if I'm having this material, that is copper coated steel or zinc coated steel, having the same diameter of 17 mm, for copper coated, we will be maintaining a 250 micron coating, whereas for zinc coated, we will be maintaining 80 to 100 microns coating. But the rod diameter is the same. In this case, even though the rod diameter is the same, the current carrying capacity of copper coated steel won't be the same as of zinc coated steel rod. Even though the difference is mainly because of this coating, that too in terms of microns, it is 250 microns, this is only 100 microns. Even though the difference is mainly because of this microns, the current carrying capacity will be, there will be a huge difference in the current capacity. And the reason behind this huge difference is the fusing temperature. So for copper, the fusing temperature will be 1084 degrees centigrade, whereas for zinc it is only 419 degrees centigrade. So for example, if I'm providing huge current, then the rod can withstand this, but the zinc over this MS will get peeled off. So the fusing, because of this fusing temperature, even though the core materials are of same dimension, the current carrying capacity of copper coated rod will be always higher than this current carrying capacity of zinc rod. So this is the calculation for comparison. So if I'm taking this hot dip galvanized rod for 17 mm dia, the current carrying capacity is around 10.9 kiloamps. Whereas for the same 17 mm dia, the current carrying capacity will be around 21 kiloamps. So the current carrying capacity is almost double the times. The main parameter which makes a difference is the fusing temperature. So when evaluating this coated materials, we should not evaluate only that whether the rod is able to withstand the fault current or not. At the same time, we need to ensure that whether the rod is able to withstand the fault current without any damages to the coating also. The primary purpose of providing coating is to protect it from this corrosion. If the coating got peeled off, then the corrosion protection won't be ensured, and hence the material may corrode much faster. So when we are evaluating this coated materials, we need to ensure that the coating is also not damaged during this entire process. So even though the core material is of same dimension, like 17 mm in this case, even though the core material is same, depending upon the material which we are coating, the current carrying capacity will be differing. So even though the difference is mainly because of 100 microns, the current carrying capacity is almost double for this copper coated rods. So we cannot simply tell that the current carrying capacity will be depending upon the cross section area. Since the cross section area of 17 mm dia HDGI rod and 17 mm dia copper bonded rods are same, the current carrying capacity also will be same. We cannot tell like that because the parameter which differentiates these two things is the fusing temperature of copper and the fusing temperature of zinc. So the third step is the tolerable step and touch voltages. So why we are giving much more importance to step and touch voltages? Our human body is more sensitive to this currents of 50 to 60 hertz frequency. So our body will show some more resistance towards this DC current. At the same time, if the frequency is lesser and if the frequency is higher also, our body will show some more resistance. But our body is more vulnerable to this 50 hertz frequency. So apart from that, the other parameter which influences the damage to human body or the magnitude and the duration of this fault current. So if there is a fault current of 1 milliamps flowing through our body, we will be having a slight tingling sensation. If the magnitude of current is increasing from 1 milliamps to 6 milliamps, that is called as let go current. So let go current in the sense, we will have the sensation that current is flowing through the body, but we will be having this consciousness to remove our hand. If our hand is floating, we can remove it and we can let the remove the hand from this engaged object. So that is called as let go current. But if the current magnitude is 25 to milliamps, it will be more painful. And if the current magnitude is 60 to 100 milliamps, it will be very much dangerous. It may result in ventricular fibrillation or stoppage of heart also. So here everywhere the current rating is in terms of milliamps. So because of the step and touch voltages, if some few milliamps is flowing through our body, we may feel electrocuted. So that is the reason we are giving more importance to the step and touch voltages. So if the current value of 30 milliamps is flowing through our body, we may get electrocuted. So the magnitude of 30 milliamps itself is sufficient for causing the sufficient damage to our body. So the parameters on which the damage depends upon are frequency, magnitude and duration of the fault currents. And one of the important points that we have to note when we are working with this IEEE 80 is IEEE 80 is one of the standards which highlight that earth electrode resistance value does not have direct impact on the safety. So they have clearly mentioned that the low substation ground resistance itself is not a guarantee of safety. So for example, if I'm working with some substations, they will tell that if you provide two earth electrodes for body and two earth electrodes for neutral, that will be sufficient for the protection. So if earth electrode resistance is the only parameter, then if I'm working with some site conditions which is having a resistivity of 10 ohm meter, then if I install only one earth electrode or two earth electrodes, then in that case I can achieve this resistance value of 1 ohms. But whether these two earth electrodes is sufficient to maintain the step voltage and touch voltage, that is the question. So even if the resistance values maintain less than 1 ohm, we cannot ensure that it is safe. So they have clearly mentioned that even if the value is low, we cannot ensure that we cannot provide guarantee for the safety. So they have also mentioned that there is no direct relationship between the safety and the ground resistance value. Even though in some cases, if the ground resistance value is higher, the design will be considered safe if the step and touch voltages are within the limit. So if I are working with the designing of substation, the two important parameters that have to be considered are the step and touch voltages, and the ground resistance won't have much importance on ensuring the safety of your personnel. So here we can observe that a substation with relatively low ground resistance may be dangerous in some cases. In some cases, even though the ground resistance is lower, it will be considered danger. So the ground resistance value does not have a direct relationship with this safety. So only with this lower ground resistance value, we cannot tell that the site is safer. We can go on. So that is not the case. If you are going for substation, the designing parameters of equipment touch voltages only. So this is how we will be calculating step and touch voltages. So it will be a little bit made of a complex normal calculation only. So here what is happening? The fault current is flowing through the body and it will be disturbed to the current only. So here the foot resistance, there are two options are there. The current can discharge from one foot to another foot. So if two resistors are connected in parallel, RF is nothing but foot resistance. Since we are having two ports, the discharge will be taking place between the two ports. And there are two parallel paths, and if the resistance is same, the effective resistance will be RF by 2. So in this case, the Z terminal will be equal to RF by 2. And if I substitute this value, I can get the E-touch voltage. Touch voltage formula will be IB into R because 1.5 rho. So if I am going for the step voltage, if there is no direct contact and the current is flowing from one foot to another foot. So in this case, if one person is standing, RF is nothing but the foot resistance, he will be standing like this. So the current will be flowing in this loop. So in this case, this 2 RF will be considered as series connection. So the Z terminal will be equal to 2 times this RF. In the previous case, the touch voltages, 2 resistors are connected in parallel, but here the 2 resistors are connected in series, again the Z terminal will be equal to 2 times RF, and the step voltage formula will be IB into RB plus 0.60. So using this formula, we can calculate the step voltage. So if you closely observe the substation, we will be providing a layer of high resistive gravels on the substation. So the ultimate reason for providing this gravel is we have to increase the contact resistance between the foot and the surface. So for example, in earlier case, some person is standing on the soil, and in both the cases, in the previous images, you can observe that for step and touch voltages, we are considering the resistance of the body alone. We are not considering the resistance of the shoes if they are wearing, or if they are wearing any gloves. That resistance of the gloves is also not considered. Resistance of the shoes are also not considered. Let us consider this is the soil, and if one person is standing here. So in this case, here he is making direct contact with the soil. So if the ground potential is increasing, the potential between the 2 foot also will get increased. So in order to avoid that, what we are doing is we are providing a high resistance layer. So if this high resistance layer is there, if the person is standing, he will be standing on this high resistance layer. So because of this resistance of this particular layer, even though the soil resistance is increasing, the same voltage won't be reflecting on the top of this resistance, high resisting layer. So because this resistance will be acting as the resistance of the foot also. This resistance will get added to the foot resistance. So because of this high resistance layer, we are increasing this resistance, and hence the current flowing through this body will get reduced. So in this case, even though if he is making contact with any structure, then apart from the resistance of body and resistance of the foot, the resistance of the layer also has to be considered. So we know that V is equal to I into R. Here the resistance voltage is constant and the resistance is increasing. So if the resistance is increasing, means if the resistance increases, I value reduces. So, for example, within this layer, if almost 20 milliamps of current is will be flowing through the body, and if I am providing this layer, then the 20 milliamps may reduce to 10 milliamps, and hence the severity of damage will get reduced. So, by introducing this highly resistive layer, we are bringing down the value of current that might be flowing through the body, and hence we are reducing this impact of further, and we can ensure the safety of the person. So, the ultimate aim of providing this highly resistive layer is to increase the contact resistance between the foot and the surface. So, in general, we will be providing this layer of thickness 0.38 meter to 0.15 meter, which is almost 150 mm. And since we are introducing this layer, the resistance of this our human body is increasing, and hence we will be introducing a factor called CS, surface layer derating factor, and hence the overall resistance we will be including this value CS in this calculation. So in the ES, that is the slip voltage and for touch voltage calculation, in the previous formula we have not considered the surface layer yet, but whenever we are providing the surface layer, the entire resistance value will get added, and hence we have to include this value of CS in the calculations. So if we are not providing this layer, then the resistivity of soil will be equal to resistivity of the surface layer, and hence the value of CS will be considered as 1. So the standard has also provided a table which explains about this resistivity of different materials which are commonly used for this surface layer. So normally we will be going for this gravel material. So if we are going for gravel, the resistance value will be around 2 to 10 to 6 ohm meter. If in extreme conditions, if we are performing this calculation and we are unable to meet this criteria, then what we can do, instead of going for gravel, we can go for asphalt, which is having much higher resistivity values. So depending upon the site requirements, in some areas we will be having a very lesser space for this earthmat designing. So if I am having very lesser space, the another option for reducing the impact of slip and touch voltages, we can either increase the thickness layer, surface area thickness, or either we can use materials which is having higher resistivity values. So if the gravel is not sufficient, then in the cases we can go for either asphalt or concrete which is having much higher resistivity values. So if we are calculating this tolerable step and touch voltages, including the CS value, in the previous formula, we did not consider the value of CS, that is surface layer derating factor. But if I consider that, then the formula for calculating the step and touch voltages are here only. So if you closely observe this, the value is different for different weights. So for 70 kgs, the weight formula will be different. For 50 kgs, the formula will be different. So it is mainly depending upon the tolerable current limit of this human body. So if my body weight is 70 kgs, then I can withstand little the Falcon to little more extent. So, but the thing which we have to consider is it is in our control because the substation will be a closed environment. So we can have the control that who are all the person who can enter into the substation. So if we have a strict rules that only person with weight of 70 kgs and above will enter into the substation, then we can go for this calculation with 70 kgs. But in our case, most of the people won't be equal even up to 70 kgs. So in those cases, we cannot restrict the people who are lesser than 70 kgs to enter the site. So in those cases, we can go for this 50 kgs calculation. So considering the safety point of view, it is always recommended to go for this 50 kg because we cannot ensure that all the person entering into the site are greater than 70 kgs. So if I am performing the design by considering 50 kgs, then the person who are 70 kgs also will be the safe. But if I am considering the 70 kg for designing, then those people who are lesser than 70 kgs, I cannot ensure the safety of the people. So the same thing is applicable for step voltage also. For step voltage also, the value will be different for people with 50 kgs and people with 70 kgs. So for the safety point of view, it is recommended to go for the 50 kgs weight. So the next step is performing this initial design. So the first step what we can do is based upon the area availability, we can have a rough estimate like if the area is 70 by 70, we can go for initial stage. We can have the mesh size of 5 meter cross 5 meter or 10 meter cross 10 meter. So there is no regulation that I have to begin with 10 meter spacing or 5 meter spacing. So based upon the area availability and the soil resistivity value, initially we can go with this assumption. So let us try with 10 meter spacing. Then I have to perform this calculation with 10 meter spacing and I have to calculate what will be the resistance value and I have to compare those values with the tolerable values. Like I have to calculate the value of step and touch voltages for this initial design. If the step and touch voltages are within this tolerable limit, then I can maintain the values. If the step and touch voltages are above the values, then I have to reduce the spacing. For example, if I take this value as an example, so 70 meters is there. So here initially we are providing some sufficient spacing. So if I'm performing this calculation and I found that this design is all not sufficient, then what I will do, I will be placing conductors in between. So initially if it is around 5 meters, then what I will do, I will change the calculation and reduce the spacing to around 3 meters. So if I'm placing one conductor at every 3 meters, then the more amount of conductor will be required and hence the potential will be almost maintained. So we have to repeat the calculation with reduced conductor spacing. So again I have to perform this calculation and I have to find the step and touch voltages and I have to compare the step and touch voltage with the tolerable limit for ensuring this safety. So the final design will be achieved only if the step and touch voltages calculated are less than this actual values. So the calculation everything has begun by assuming that a circular disc is placed on the surface of this earth. So the entire calculation, the basic for this entire calculation is a circular metal disc is placed at zero depth. So from this assumption only they have derived this entire formula. But here if you take this mesh size, the in between area are open only. So the circular area is not maintained. At the same time, we are not burying at the zero depth. We are going below the soil level. So this reduction in the area and the increase in the depth, we have to make some modifications in the formula. So from this basis and because of this actual conditions, we are deriving this formula and the final formula which we are arriving for calculating the value of Rg is the grid resistance is rho into 1 by Lt into 20. Here you can observe that the three important parameters are Lt, that is the length of the conductors, area is the over area which is available for this earth mat, and H is the depth of the grid. So whether I am going for 500 mm burial or I am going for 600 mm. H is the depth of burial, A is the area availability, L is the total length of the conductor which is used for this earth mat. So if I am reducing this spacing, then the value of LT will be increasing. So if the value of LT is increasing, then the value of resistance, grid resistance will be reducing. So the most important thing is we have to calculate the grid current. So even though we know that the most worst fault current will be at voltage short circuit fault of three phase to ground fault, but the three phase to ground fault is one of the rarest phenomena that won't happen more frequently. So even though that is the worst case, but since that won't happen in their power system, they consider that single line to ground fault and line to ground fault as the worst cases in substations, and they have provided the formula for calculating this fault current for both the cases. But most of the cases, the customer will be having this fault level for the particular substation, and we can skip this step if we are having this fault level like 40 kF for 1 second or 25 kF for 3 seconds. So this the customer itself will be having this. So if they are having it, then this particular portion of the formula can be skipped. So we are calculating this fault current, but we cannot ensure that the entire fault current will be flowing into the soil, because if I take one particular substation as an example, we are having lot of feeders and we are having all the transmission lines will be coming into this picture. So if you take one particular transmission line, we will be having ground wire or shield wire on top of this transmission towers. So this transmission towers ground wire also will be connected to this particular earth mat. When any fault is happening, this fault current will be returning to the source, and we also consider that the returning will be taking place through the soil, but it is not mandatory that all the fault current has to return to the source through the soil. So if I'm having a substation and it is having lot of feeders, then in that particular case, let us know this is a substation and we are having towers here, and in the top of tower we'll be having this ground wire. Similarly, here also we will be having towers. So here we are having this equipment, and we are burying to the earth mat. So if some fault is happening, this current will be returning to the soil, and some current will be returning to the source through the soil, and some portion of the current may return to the source through the transmission line ground wire. So here some portion of current is diverted to the source through the shield wire or ground wire. So the entire current won't be flowing through the soil. Some portion of the current will be flowing through the transmission line ground wire, and the remaining will be flowing through the soil. So when we are calculating this grid current, so there is no need for calculating this entire fault current. Some portion will be flowing, and to maintain this particular portion that is flowing through the soil, we are maintaining the factor called SF, that is fault current division factor. So based upon this SF factor only, we will decide how much percentage of the current which will be flowing through the soil to the source. So when performing this calculation, it is not required to calculate this entire performance for the entire fault current. Only the portion of fault current that is returning to the source through this particular earthing grid has to be considered for this calculation. So when we are having a number of transmission networks in the particular area, then the current will be having multiple parallel paths. If the multiple parallel paths is higher, then the portion of current that will be returning to the source through the soil will get reduced. So if I am working with any substation which is having lot of feeders, then the SF value will be different, and hence based upon the SF value, the grid current also value will get reduced. In general, we will be considering the SF value as 50% to 60%, but there are certain criteria conditions where the SF value was even lesser than 0.3 also. So it depends upon each and every site conditions. We don't have any general thing for deciding whether what will be the SF value. So we have calculated this value of actual step and touch voltages, then we have calculated the value of GPR, then we have calculated the value of IG also. Then now we have to calculate the what will be the actual step and touch voltage on this particular site conditions. So the actual step and touch voltage on this particular site conditions can be calculated by using this formula. So the step voltage, that is EM, they are mentioning is the mesh voltage. So mesh voltage is the maximum step voltage in this particular substation condition. So EM can be calculated by using this formula, rho into Km into Ka into Ig by Lm. And for each and every parameter, they have provided the formula for this calculation. So using this formula, we can perform the calculation and we can find what will be the actual step mesh voltage for this particular site condition. Similarly, the actual step voltage can be calculated by using this formula. So the different parameters involved, the standard has mentioned the procedure for calculating the different parameters also. So Km they have provided formula, Lm is the grid conductors length of the mesh conductors we are using, and here the values mainly depends upon the different parameters. One is whether we are providing ground rods for this grid or not. So it is not mandatory to provide earth rods for this earth mat. So even if there is no earth rods are provided, the design can be considered as safe if the step and touch voltages are within this tolerable limit. So for this particular earth grid, whether we are providing ground rods or not. And second one, if I am providing ground rods, whether I am placing this ground rods randomly or whether I am placing this ground rods along the perimeter of the grid or I am placing it along the corners of the grid. So depending upon the position of the ground rods also, the parameter will be different. And third one is shape of the grid. They have explained about square configuration, then rectangular configuration, then L shape. So depending upon the shape also, the values of the parameter will be different. So based upon these different parameters, the values of the factors will be different. And the standard has already explained about this procedure. So if it is a square, what will be the value of n? So if it is a rectangle, what will be the value? If it is a L shape, what will be the values? So if I'm having a square grid with earth electrode only on this perimeter, then what will be the value? If I'm having a square mesh only earth electrodes at the random places, we are not providing on the corners, then what will be the value of the parameter? So they have provided a detailed explanation about for each and every uh, different connection configurations also. So if we are performing this designing, so first initially we have calculated the tolerable value, then in the last step we have calculated this actual values. So we need to ensure that the actual step and touch voltages are within this tolerable value. So if the actual step and touch voltages are within the tolerable value, the design will be considered as safe. In case if the actual values are greater than this tolerable value, then what we have to do? We have to redesign this earth mat and we have to ensure that the resistance value, that is the step and touch voltages, are within this tolerable limit. The standard has also provided few points for reducing this uh, step and touch voltages within this tolerable limit. So the points provided by the standard for modifying this designing are: first one is reducing the total grid resistance. So, so the main problem is because of this GPR. GPR is because of the GPR only the step and touch voltages are coming into the picture. So GPR is nothing but Ig into Rg. So if I reduce this Rg, then the value of GPR can be reduced. So that is the reason the first point they have mentioned is reducing the total grid resistance. So the total grid resistance can be reduced by two methods. So the first method is increasing the area. So for example, in the initial design, I have considered 70 meter cross 70 meter. If the value is still higher, then what happens? What can we do? We can increase the area from 70 meter to 90 meter. So if I'm having this 90 meter cross 90 meter, I'm increasing the length and width and we are having more area. Since the area is increasing, the conductors which we are using for the grid also will be increasing and hence the resistance value will get reduced. So if the resistance value get reduced means the R value is reducing, but and hence the GPR also will get reduces. So by increasing the area, we can reduce this resistance value. But in most cases, it won't be possible because of the space constraints. So in areas where we don't have sufficient spacing, then the alternate method provided by the standard is by using deep driven earth rods. We can provide earth rods at different places. Like we can initially, if there is no earth rod in the design. So I have mentioned in the previous slide, it is not mandatory to have this earth electrodes. So if I am performing this calculation and found that values are higher, then what I can do? I can go for this earth electrodes. So initially I can go for earth electrodes at random places. Then I can check what is the values. So still if the value is not achieved, then I can increase the number of earth electrodes. I can increase from, if initially if it is 4, then I can increase from 4 to 8. So even if increasing the earth electrode numbers, it is not possible to achieve this value, then what I can do, I can increase the length of the earth electrode. Initially if I'm going for 3-meter rods, now what I can do, I can increase the length from 3 meter to 6 meter, or 6 meter to 9 meter, or 10 meters. Similarly, I can increase the length of the rods to achieve this lower step and touch voltages value. So one point for reducing this RG value is to increase the area, and another provision for increasing the, sorry, for reducing this resistance value is by using deep driven earth electrodes. So we can increase the number of rods, or we can increase the length of the earth electrodes to maintain the step and touch voltages within the limit. So the second point is by using closer grid spacings. So if I'm increasing the area, in that case area, number of conductors is increased. Because of this increase in conductors, we are reducing this resistance value. So the another option for reducing this RG value is by providing closer spacings. So if in this initial case, if I'm having a spacing of around 5 meters, if I'm having this 5 meter spacing, if the value if I'm calculating is still higher, then what I can do, instead of 5 meters, I can go for reduced area, reduce the spacing. So if I'm increasing, reducing the spacing means the conductors required will be higher. If the required conductor is increasing, then obviously the resistance will get reduced. So if I'm increasing more conductor, then the resistance will get reduced. So this is another option for reducing this RG value. So by reducing the spacing, I can maintain this step and touch voltages within this limit. So the step and touch voltages within this limit we can maintain inside this substation. But one more problem will be coming into the picture regarding to this boundary, that is the perimeter area. So if some person is standing outside the substation, and if he is making contact with this fence or any structures on the substation area, then the person who will be standing at the remote on the soil will be at different potential, and the substances on this earth mat will be at different potential. So because of this difference in potential, current will be flowing through the body and he may get electrocuted. So the potential along the perimeter of the building also has to be considered while performing this designing. So the standard has provided 3 methods for maintaining this potential along this perimeter and to ensure the safety of this person who will be working near this perimeter. So one such thing is the grid conductor can be provided outside the fence area. For example, if this is the grid area, then I have to provide this fencing inside this grid area. So even though if some person is making contact with this structure, then the person will be standing in this grid area only. So if he is making contact, this will be at the same potential of this person. So there won't be any impact due to this touch potential. So the fence can be brought inside this grid conductor area. And the second one is increasing the density of ground rods. So if I'm increasing the density of ground rods on the perimeter, the voltage can be maintained to lower values. So by increasing the density of ground rods along the perimeter, we can maintain this voltage at the perimeter at a lower value. And another option will be providing closer spacings near this perimeter. So if this is the perimeter, then instead of maintaining uniform spacing for the grid, what I can do is I can provide very closer spacings near this perimeter area. So here I am maintaining very closer spacing, but in the inside area I won't be maintaining the same. I will be providing higher spacing. So the closer spacing will be maintained only at this perimeter region, whereas in the internal area the closer spacing won't be maintained. So by reducing the spacing on this perimeter area, we are bringing down the voltage levels to tolerable values. So the safety of the persons on this perimeter area can be maintained by using these 3 steps. And the next step is diverting the fault current to other parts. So as I mentioned, if one substation is having lots of feeder lines, then the ground wires or shielded wires of this transmission lines will be connected to the network, and more amount of fault current will be diverted through this ground wires or shield wires. So the portion of current that will be entering into the soil will be lesser. So when we are performing this calculation, we will be performing this calculation only for this current that will be traveling through the soil to the source. And since the current is diverted to the ground wires or shield wires, the current portion of the current that will be traveling through the soil will be reduced, and hence the value of Ig will be reduced. So as I mentioned, the value of GPR is nothing but product of Ig into Rg. So if I take the first two points, so here we are reducing the value of Rg. But in this third point, I am reducing the value of Ig. And the fourth one is limiting the total current. So we won't go for this method mostly, but that is also one option is available. We can make some arrangements for reducing the fault current levels on the particular sections. And final one is restricting the access to limited areas. So here we are considering the safety of the person, and by providing the fences and by restricting this access to people into the substation area, we can avoid this damages. So restricting this access will be one of the solutions for reducing the damages due to the step and touch voltages. And another one is what we are doing is we are comparing this tolerable value and the actual value. So if the tolerable value, if the actual value is less than this tolerable value, then the design will be considered safe. AT is nothing but actual value. If the actual value is lesser than the tolerable value, the design will be considered safe. In this all the parameters, what we were doing is we were discussing about reducing this actual value. How can we reduce this actual value? But under this, if there is no option available for reducing this actual value, then what I can do is I can increase the tolerable value. So if I don't have any facilities for reducing this actual value, and if I'm increasing this tolerable value, then the criteria can be met. So the last point explains about what are the provisions available for increasing this tolerable value so that I can achieve this safer design. So the point provided by the standard for increasing the tolerable step and touch voltages or reducing this fault clearing time. So if you closely observe, all the things which we have mentioned mainly depends upon the fault duration. So if I reduce the fault clearing time, which means if I'm providing some switch gears with very fast acting switches, then this, because of the fast operation, the fault clearing time will be reduced. So because of by reducing this fault clearing time, I can reduce the tolerable step and touch voltages. Then by using the surface material. So I have shown one table which explains about the resistivity for different materials that are commonly used as a surface material. Initially, if I'm using this gravel, then if I found that the design cannot be met, then I can change the material from gravel to this concrete, or I can either change from gravel to asphalt. So if I'm increasing this value, then the tolerable value will get increased. And the another option is increasing the thickness of the layer. So if I increase the thickness of the layer, then the overall resistance will get increased. Because of this increase in overall resistance, then the tolerable step voltage and touch voltage also will get increased. So by using these three values, we can increase the tolerable limit. So if I take this modification, so the standard has mentioned about 3 points. The first one is related to reducing this Rg. It's nothing but grid value. The second one is by reducing this value of Ig. And third one is increasing the value of tolerable limit. So by using these three methodologies, we can ensure that the system, the design which we are providing is safe. So the options provided by reducing this Rg is we can either increase the mat sizing, or we can provide deeper earth electrodes, or another thing is we can provide closer spacing. For reducing this value of Ig, the commonly used method, we are not reducing it actually, but what we can do is if I'm connecting this shield wire of transmission lines, then some portion will be getting diverted. So the reducing Rg, the parameter involved is SF. fault current diversion factor. Based upon this, the fault current value will be changing. And third one, if I cannot make any modifications on the system to reduce this actual value, then what I can do is I can make some modifications to increase the tolerable limit. So if I'm increasing this tolerable limit, then I can make this design as safe. So they have even provided 3 steps for increasing the tolerable limit also. So by using this recommendations provided by the standard, we can ensure that the criteria of step and touch voltages are met, and we can ensure that the design is safe. So in all these steps, around 12 steps, if you closely observe, nowhere we have considered the grid resistance value. So the grid resistance value is considered only for this GPR. It is not considered for ensuring the safety of this person, or it is not even considered for ensuring whether the design is safe or not. So the value of RG is maintained only because of keeping this GPR in control. So RG is not the deciding parameter. The deciding parameters in EarthMat system is the step and touch voltages. So here we have shown the sample calculation from the standard. So here in the initial stage they have taken square configuration of earth grid, and without earth electrodes they have taken. So square configuration without earth electrodes they have taken, and they found that the values of step and touch voltages are not within the limit. So the mesh voltage calculated is higher than the tolerable limit, that is 1002 is the mesh voltage and 838 is the actual value. Since this mesh voltage is higher than the tolerable limit, the design is not safe. So we are making modification. The modification they did was they have provided earth rods. They have provided earth rods for reducing this touch voltages. So after installing earth rods, the values has become reduced. So this is the result of the calculation after this modification. Here you can observe that grid resistance value is 2.52 and step voltage is 756 voltage, whereas the actual tolerable value is 838. So 756.2 volt is lesser than 838.2 volt, and hence the design is safe. So they have concluded that a safe design has been obtained. So in the safe design, if we closely observe, the resistance value is 2.5 volt, sorry, 2.52 ohm. So from this conclusion, we can observe that even though the earth resistance value is not less than 1 ohm, the design can be considered as safe if the step and touch voltages are within this tolerable limit. So I have just provided the output of this calculation alone. If I want to explain this complete calculation, means it will take another half an hour. So I have just shown this output of this calculation alone to highlight the point that for this safe designing, the earth resistance value is not the designing parameter, whereas the actual designing parameters are step and touch voltages.